All right. Okay, we're gonna go over just some sort of basic trig, how to think about the values of sine, cos, and tan, um, how to solve some simple equations uh, involving trig functions. We won't get too deep into it, but just a bare bones, how to think of the values. If I tell you sine of uh, 110 degrees. Is that a positive quantity? Is that a negative quantity? Is it zero? Could we tell exactly what the value is? Is it a special value? Um, all right. So my preferred method here for thinking of the unit circle, or thinking of trig, is through the unit circle. Um, we draw out our let's draw this out. Let's draw our circle out. Okay. All right. Um, there we go. Okay, and now you might remember uh, here. Oh, and I guess a unit circle typically in math, whenever we say unit, it usually means that something is one. Uh, so when we talk about the unit circle, um, we're saying the radius is one, right? So this distance is one. In fact, the distance from the center to any of the points along the edge is one. Uh, okay. Remember as well that um, we measure the angle in this way, counterclockwise from the positive x-axis, right? So if I were to draw sort of a ray from the origin to this point here, this angle would be the angle that we typically talk about. That's our theta. Um, that would be a positive angle because it's in the counterclockwise direction. If you had a negative angle, it'll extend in the clockwise direction, or we'll sort of think of it in the clockwise. Um, but anyways, we have a point on the circle like this, and the way to think of our sine, cos, and tan values is that sine, uh, oops, not that, is that cos of theta is the x coordinate of that point, and sine of that theta is the y coordinate of that point, whatever that happens to be. And tan theta is the slope of that line. Um, okay, with these basic ideas, and with understanding where the angles are. So okay, so like if we haven't moved at all, I guess this would be zero radians. I suppose we should talk about radians, not degrees. It would be 0 degrees as well, but uh, this is 0 radians. Remember, uh, one full rotation is 2 pi radians. Uh, I usually like to get into a point here that 1 radian is the distance you move along the circle if you travel 1 radius. So, like if I think about, okay, there's my radius, and if I travel about that far on the circle, so that distance is r, then the angle formed here is 1 radian. Right? That's how radians are measured. And then if we then remember our circumference is 2 pi r, that's the circumference of a circle, the distance all the way around. Well, that's literally telling us that we need 2 pi radii or radius. Well, radii is the technical term or the correct one, but 2 pi radii to travel all the way around the circle. That's why one full rotation is 2 pi. Um, so where I have 0, this could also be 2 pi. I could also go backwards 2 pi, which would be like negative 2 pi, or 4 pi is also what that point is. If I travel 2 pi really from any point, it'll just leave me where I started. Well, then this means that a half rotation, so if I was to go from the positive x-axis to the negative x-axis, a half rotation is just pi then, half of 2 pi. And a quarter rotation is half of that, so pi by 2. Uh, uh, 3/4 rotation is 3/4 of 2 pi, or it's pi plus 2 pi. But 3 pi by 2 is that one. Okay. So just with this, we should be able to think of at least the values of sine, cos, and tan on at least on the cardinal positions, like north, west, east, south. For instance, if I was asking, let's say, like, what is sine of pi? Um, well, I think of the point on the circle where with that angle. I've visualized it here, right? That's a pi rotation. So I'm at this point here. Um, well, because this is the unit circle, um the coordinates there need to be -1, 0. It's on the x-axis, so of course the y-coordinate is 0, and then like everything is in the x direction. So x must be the same as the radius, which is 1 in this case. And then again, I've told you that sine is the y-coordinate, so sine of pi is 0, and cos of pi, which is the x-coordinate, is -1. And then I could even think about, okay, what about tan of pi? What's that? Um, Tan of pi, well, if I join that point with the origin, and I think of that line connecting the point and the origin, what's the slope of that line? Well, it's 0. It's flat. It's horizontal, right? So tan of pi being the slope of that is 0, right? There's 3 values for sine, cos, and tan that we should be able to say, right? And another point here too is like this isn't just useful or like just like okay, what if they asked me what is this equal to? Sometimes you do work in calculus or in math in general, and you'll have terms like these popping up in your work. You'll be have sine of pi, tan of pi, or sine of some other angle. You'll have these trigonometric terms showing up. And if you don't recognize that it's can be written in a much simpler way as just like, oh, sine of pi is 0, so it might not add on to anything, or it might not change something if it adds on. If you don't realize that these can be represented by simpler values, uh, then you won't be able to simplify the work you have nicely. You won't be able to get the sort of cleanest answers, and just your thought process will be really messy because you might have more things floating around in your uh, uh, calculations than you need, right? This is really part of the reason why we need to be familiar with the trig functions. You need to remember the special values. They come into solving equations as well. Um, okay. But anyway, so this should at least give us the cardinal positions. Again, like I said, northwest, east, south. It also gives you a reason why, like you know, or you might know that the graph of tan kind of looks like this, right? That's tan of x approximately. You know, within a rough sketch. And where are these asymptotes? They're at -pi by 2 and pi by 2. Well, why is that? Well, because as I approach the angle of pi by 2, so as I approach this point, the lines that I have sort of leading up to that point, they're getting steeper and steeper, right? And the slopes of those lines are uh, growing unboundedly. That's why the function tan has these asymptotes. That's why it approaches infinity as it approaches pi by 2. It approaches negative infinity as we get to, from the right, at least, of negative pi by 2, because of the same reason, just opposite. If I'm going to pi by 2, my lines look like this, right? Those are also steep lines, but they're steep with a negative slope. They're going to a negative infinity. Okay, so um, we have that. Next thing you need as well, typically, are a couple other special values you need to recognize. Um, uh, these are we're going to focus on the first quadrant. So I have my circle here. We have pi by 4. We have, oops, we have pi by 3, and we have pi by 6. We have those three, and then again, this is our pi by 2 and our 0. Um, these are three special values within the first quadrant we need to be familiar with the values of our trig functions at. And then there are symmetric versions of these in the other the other three quadrants, right? If you think about, okay, there's like a there's like an angle here that maybe if that's pi by 6, then sort of this on the other side, that is must be pi by 6. But then if that's pi by 6 and it makes up pi, I must have 5 pi by 6 on this side. So that would be, say, an angle of 5 pi by 6 measured in the standard way. Okay, but I have these special angles in the first quadrant. And we need to think of the values of sine and cos and tan in these. Actually a couple ways that people generally um, remember these, but like you might remember special triangles. There's two triangles we can draw and just remember their sides, and then with SOHCAHTOA we can get sine, cos, and tan from there. Um, there's maybe you just remember a chart of values, or maybe you just remember like a picture of values. Uh, um, I kind of like this. This is my preferred method here. Is let's say if we were doing sine of pi by 3, cos of pi by 3, and tan of pi by 3, right? Um, they're all gonna be well for sine and cos, they're all gonna be root of something divided by 2. And for tan, it'll be root of something both on the top and bottom. Okay. And what those somethings are, uh, well, uh, is this. For sine, you start at pi by 3 and you go to the right and you think of how many lines do I cross? Or there's a nice thing here too, that if you kind of like look at your hand, like your left hand, you can make the angles in the same way. Like there's my angle of 0, pi by 6, pi by 4, pi by 3, pi by 2. And you can imagine, okay, I'm at pi by 3. I go down across 3 fingers. There's a way we can draw it on our hand. But yeah, I start at pi by 3 and I go to the right. How many lines do I cross? 3. That's what I put in the square root box. And that's also what goes in the numerator of the square root box for tan. For cos, it's the same thing, just in the other direction. And I cross one line there, so it's root of 1 over 2. And tan of pi by 3 The denominator there is that cos value we got there. Okay. Um, all right. So hopefully with this you can at least visualize or yeah, visualize honestly. A lot of times when I do trig problems, and we'll do a problem in a second. A lot of times when I do trig problems, I will just sort of draw out a circle, think about where intersections are, think about what's my x coordinate, what's my y coordinate, what's my slope of my ray, right? Um, Anywho, yeah, let's do an application here just to try to cement this. So we'll clear this. Let's say you have some equation that you want to be satisfied, and we'll say it's 1 minus 2 cos theta equals 0, right? Um, uh, Not to get too far off topic, but with a lot of sort of function equations where you have like cos or sine or tan or exponentials or log, I would encourage you to try to solve for the function first, and then go from there. Either think of the special values, use the inverse functions, uh, but we'll get to that later on. Um, if I take this and I'm going to try to solve for the cosine theta. So I'm going to subtract 1 from both sides. Then I'm going to divide by -2 on both sides. So I get cos theta equals negative over negative is positive. So that's 1/2. Then I'm going to, here I could do the inverse function. I could say like theta is arc cos, but we won't get into inverse functions right now. No, here for this again, I'll draw a circle, draw my sort of unit circle idea. Cos, like I said, is the x coordinate of a point on the circle. So this equation is kind of like asking when is x equal to 1/2 on our circle. And if I think of that line of x equals 1/2, where it intersects the circle will be the solutions, will represent the solutions rather. So like I have a point like that with maybe an angle measured from there, and I'll have a point like this where I could go backwards to that angle. I could also go forwards to maybe that. Um, let's talk about the negative, the negative solution, I guess, first. Okay, so I could draw this out and I can see where the solution should be. I can also see like how many solutions I should have at least in one rotation. Something to remember too with trig is you often get multiple solutions in kind of two ways. One way with this sort of symmetry that there's like a point on the top and a point on the bottom that satisfy this intersection. For sine, it'll be like a point on the left and a point on the right, because then you're thinking of when is y equal to a particular value, and that's a horizontal line. Tan would be kind of symmetric through the origin, because you're thinking of a line with a particular slope. But I draw this, and I want to then think about, okay, what's my angle? Do I have are one of my special values going to give me this? And we actually just calculated it previously, right? That cos theta. Um, I mean, this looks like root of something over 2, although it doesn't always have to look exactly like the thing that you have. Like for instance, if this was 1 over root 2, you might struggle to think of like, okay, root of something over 2 doesn't seem to match that because the root's on the bottom. But it's actually the 2 that would be inside here, and that's because root 2, we could represent 2 as root 2 times root 2. So it's like the root 2's cancel and it's 1 over root 2. So sometimes you might get not these sort of special values written in different ways. that you don't recognize with however you memorize them. And we need to fall back on our more fundamental algebra skills to simplify or rewrite what we have. But regardless, in our case here, um, we do have something like root of something over 2, as long as we recognize that root of 1 is 2. And so if I think of my hand, okay, if I start at that at my ring finger and go to the my pointer finger, sorry, and go to the left, I cross one finger. That was the pi by 6 angle. So I know uh, I can recognize my special value here for theta. Oh, sorry, not pi by 6. That's 0. That's pi by 6, pi by 4, pi by 3. My mistake. Okay, and so that's this angle here. That's pi by 3. Um, and again, because it's a circle, it's symmetric horizontally, vertically. That means the angle, the sort of angle at the bottom, that is going clockwise, so it's a negative angle, but that angle is also pi by 3, just negative if we think of the angle measured standardly or from the standard position. So that means I at least have theta equals pi by 3 and theta equals negative pi by 3 as 2 answers. There's more, because again, I said, right, if I'm at a particular point and I travel all the way around, then I still remain at that point. So that means pi by 3 plus 2 pi is also a solution. Negative pi by 3 plus 2 pi is also a solution. And in fact, you might remember from high school, you write a general solution as just adding any number, any integer number of pi by 2s. So I might have this as my general solution with k as an integer, right? And this is a whole bunch of different answers that we could consider. Maybe some are more appropriate for certain situations, or maybe that goes further beyond that. But just solving a simple trigonometric equation, recognizing special values and the symmetry of the circle, as well as this visualizing intersections, right? Again, if you have a thing with like sine theta equals a number, you're going to draw your circle. You're going to draw a horizontal line of like y equals whatever that number is. The intersections give you your answers. Like you saw here, if I have cos of an angle equals a number, I draw my circle. I make a line where for x equals whatever number that is, those intersections give me my solutions. And if I want tan theta, if I have some tan theta equals a number, I draw the circle. Now I'm going to draw a line that has a slope of whatever that number is. And then those intersections represent my angles for that would satisfy this equation. Okay. All right. Hopefully that helps you work through sort of more basic trig functions a little easier, understand them a little better. Okay.